All right. Welcome to the third lecture on lattice gauge theory. Apologies about the delay in getting this to you. All right, so what we've seen over the last two lectures is that in the framework of lattice field theory, we can calculate the expectation value of some observable that we're interested in as essentially a very large but finite dimensional integral that we can do by Monte Carlo sampling. And you recall we got there by discretizing the different pieces of our action, by rewriting this integral here over the gauge degrees of freedom u. The u's are now link variables on the edges of our lattice. This becomes something large and finite dimensional. We've integrated out the fermion fields exactly, and they appear here as this fermion determinant, which is hanging out in the weighting of each gauge field u, and as fermion propagators that we saw how to contract into correlation functions. So last time we saw an example of that, how you can extract some physics observable. For example, the pion mass was what we looked at in detail by calculating a correlation function. In that point, it was a 2-point correlation function. And we saw how the Euclidean time dependence of that 2-point correlation function lets us extract the pion mass from a statistical analysis. We also saw how you actually compute that 2-point correlation function by contracting quark propagators. Okay, so in this lecture, as I sort of promised in previous lectures, I want to give a bit of intuition for the types of things you can calculate in lattice QCD, what's easy, what's not so easy, and why, as well as a little bit of phenomenology and one example in some detail. So the first question is, what kinds of correlation functions are calculated? So we already saw one example of this in some detail, and that was 2-point functions, where we had a creation operator or a source, an annihilation operator or a sink. And so we had the 2-point correlation function between that source and that sink at some different Euclidean times. And we saw how to extract the pion mass from that. In general, you can use these to do spectroscopy. So extract not just the mass of a ground state, but the spectra of an entire tower of states with some quantum numbers. You can also compute things like 3-point functions. So one type of 3-point function would be matrix elements of some local operator. So for example, you might compute matrix elements of some operator to extract, in the continuum sense, matrix elements of operators. So you might be interested in things like the axial charge of the nucleon, or more generally, things like form factors. So these are called 3-point correlation functions, of course, because you have 3 points of interest. You have the source, then you insert an operator at some intermediate Euclidean time, then you annihilate at the sink, as well as electromagnetic form factors if you want things like moments of parton distribution functions. You might want things like beta pi decay form factors to constrain CKM matrix elements. And so on. So essentially, if you can write it as a matrix element of a local operator, then there's a good chance you can extract it using a calculation of a 3-point function. You might also be interested in 3-point functions that are matrix elements of non-local operators. And so this is an example that I discussed with some of you at office hours. That you can write, for example, the X dependence of parton distribution functions or transverse momentum dependent parton distribution functions in terms of matrix elements of non-local operators in particular limits. For example, in the large momentum limit or large boost limit, you can make a relation between the light cone matrix elements that you'd really like to compute for PDFs and Euclidean matrix elements that you can write down as matrix elements of non-local operators. So it's really a way of accessing, in that example, a way of accessing something that's hard to access in Euclidean space. Those types of frameworks are called things like quasi or pseudo PDFs or TMDs. Or you might calculate higher point functions for other observables. So 4-point functions, for example, they come up if you want matrix elements relevant to, say, double beta decay. Or K bar mass difference. So they start getting more expensive and more difficult to compute as you go to higher point functions. 4-point functions can get quite computationally tricky, but you see the general picture that if you can write it as some sort of a matrix element, you can then go and compute that matrix element in terms of correlation functions. Now, something that I'll have not enough time to really go into, but I want to mention because it's important, is operator renormalization. So when we're taking not a 2-point function, but say a 3 or higher point function, a matrix element of some sort of operator, we have to keep in mind that the operators defined from the bare lattice fields are not renormalized. And so there's an additional step we have to take to connect from the lattice calculation from the bare matrix elements that you can extract to the physics that you're trying to access. As I just said, operators defined from bare lattice fields are not renormalized. So there's an extra step required. And this is true even for renormalization scale independent operators, because the lattice discretization can introduce a finite shift. So this renormalization step is really important. And in fact, in this renormalization step, you have to be careful because you've changed the symmetries of your system. When we broke our Lorentz symmetry down to, say, the hypercubic group, that also changes the way that operators can mix under a normalization. So since the lattice regulator introduces a dimensionful scale, it allows for mixing of operators of different dimension. So what that mixing really looks like is that you have some bare operator, call it O1, and this will look like some linear combination of renormalized operators. And that linear combination may come with powers of the lattice spacing in here, depending on the dimensionality of the operator. So here I've just put a to some power n, but that n, that power, that could be less than 0. And in that case, you'd have power divergent in the lattice spacing operator mixing. And that means as you make the lattice spacing smaller, as you take the continuum limit, the mixing gets worse and worse and worse. And it's harder and harder to extract the matrix element that you're actually trying to target. And so that can really complicate calculations or make some of them unfeasible computationally. So we're 0 leading to power divergent in the lattice spacing operator mixing. Which leads to complications. Okay, so typically, one way to get around this is to choose operators that are protected from these sorts of power divergent mixings by choosing them in irreducible representations of the symmetry group that we do have, the hypercubic group H4, that are have no lower dimensional operators living in the same irrep. And then you can just compute the remaining non-divergent mixings explicitly and do the renormalization calculation. So this is typically an important step, is choosing not just the operators that you want to compute matrix elements of, but also making sure that they live in protected irreps of the hypercubic group. So we typically choose operators in irreps of H4 that are protected from mixing with lower dimensional operators. And we compute the remaining non-divergent mixings. Okay, when we're doing this renormalization, ideally you want to renormalize into some scheme that is understood and can be compared with, say, experimental results. So typically you're aiming to renormalize into a scheme like MS bar. There are multiple ways of going out doing this renormalization of the non-divergent pieces. You can do it perturbatively, and that means you're using a lattice perturbation theory. You do analytic or numerical calculations of the relevant Feynman diagrams, starting with the lattice action and lattice regulated integrals. You do the same calculation in dim-reg to convert to MS bar. This is tricky. It's not necessarily well convergent, but you can do perturbative renormalization. You can also do a non-perturbative renormalization, where there's a number of different ways of doing that. One sort of conceptually straightforward scheme is to use an intermediate scheme defined in a regulator independent way. So, for example, you require some simple correlation function, some endpoint function to take its tree level value at some scale, and that defines your normalization conditions. You do that calculation numerically, and then you still need to do a perturbative matching to get to your target scheme, say MS bar. So I don't have time to talk too much about this, but I wanted you to know that this is an extra step that has to be done in the calculations. So we can do operator renormalization in multiple ways, e.g. perturbatively or non-perturbatively. Okay. So this really brings us to sort of a summary. So how does a lattice QCD calculation progress? We've seen essentially the entire workflow, but I want to summarize. And give you some idea of sense of scale, really. Okay, so step one, and these steps are really after you've defined your action, the discretization you want to use, the set of parameters you want to use. So this is after you've moved into doing a calculation on a single ensemble of gauge fields. What does the numerical workflow look like? Step one is you generate a set or an ensemble of field configurations by some sort of sampling algorithms. As we've discussed, typically that would be Hamiltonian or hybrid Monte Carlo. So you generate an ensemble of gauge field configurations. By some Monte Carlo. And for a sense of scale, typically this would take hundreds of thousands of CPU cores or thousands of GPUs. Sort of state-of-the-art calculation. So this is a really significant computational step in the workflow. Then you have to compute the propagators that you're going to tie up into correlation functions. So we want to compute things like M inverse on each one of our configurations. You would do this using an iterative method, something like conjugate gradient. And this is sort of a smaller scale calculation computationally. You probably only need a few hundreds of GPUs, but you have to do this many, many times per config, per configuration, per sample. So you might have sort of order a few thousand samples of gauge fields, but on every sample, you might compute hundreds or thousands of propagators. Okay. Once you have the propagators, you can track them into correlation functions, like the 2-point correlation function that we saw for the pion. This is, again, sort of a smaller scale task. So you need a few GPUs or CPUs. But again, you'll do this many times for each of the gauge field samples. And then you'll do some sort of fits or analysis. And as we saw, again, with the example of the pion mass, that could be fitting the Euclidean time dependence of the correlation functions to extract the spectroscopic result or the matrix element that you're trying to access. And this you can typically do at a local cluster scale. So this doesn't need the same scale of resources. Sometimes you can even do most of this on your laptop. It doesn't need the same sort of resources as these parts of the workflow. Okay, so that's the sort of workflow, the structure of a numerical calculation on a single ensemble. Remember, we talked in the first lecture about the sort of surrounding pieces of this, that once you've done a calculation for one set of lattice parameters, one lattice spacing, one lattice volume, one set of bare quark masses, you have to do it over and over again for other parameters, so you can take the continuum limit, the infinite volume limit, and so on. So on this theme of building some intuition, let's talk about uncertainties. Okay, so the different uncertainties that come in to this calculation are, of course, statistical to start with. And in some sense, that's straightforward to reduce. You have 1 over the square root of the number of measurements scaling. So as you take more and more samples of your gauge field configurations, you compute more and more propagators on those samples, take more and more measurements, you can reduce the statistical uncertainties accordingly. Then there are systematic uncertainties that come up in this last stage in the fits to the correlation functions when you're fitting the Euclidean time dependence to extract the underlying physical quantity. So here you have systematics coming from choices like the functional form of the fit. In that example we looked at, you know that the functional form is a sum of exponentials, but how many exponentials do you fit in that sum? How many can you constrain statistically, and so on? What fit range do you do? And so on. Essentially the various analysis choices that you can scan over. If you make different choices, if you use different fit ranges and get slightly different answers, how you combine those statistically, and so on. There are also systematics from all of the extrapolations you need to do across multiple ensembles. So we have to take the continuum limit, the infinite volume limit, and that comes from an extrapolation of several individual results. You have to worry about whether the pion mass is tuned to be its physical value. CSV, here I mean charge symmetry violation. Are you breaking the up and down quark masses into their different values, or are you making the approximation that they have the same value? Are you thinking about including QED into a calculation or just QCD? Again, exactly what these are will depend on the theory you're studying. Here I'm being a little bit QCD biased. What are you doing about chiral symmetry? And so on. And these, depending on what lattice calculation you're reading at, these might be neglected or they might be taken care of. When there are words in papers like complete control of systematic uncertainties, that may mean just a physical pion mass and these limits have been taken, but the light quark masses still have the same values and there's no QED, right? So that's sort of a context dependent statement and you have to be careful. These are possibly neglected. They start to become important, especially if you're looking at sub% precision calculations. Okay, so these are the types of uncertainties you should be thinking about when you're assessing a lattice QCD calculation, trying to understand how seriously you take the uncertainties, what the uncertainties mean. You want to know, have these been accounted for? Are they just so small that they're irrelevant at the scale of the other uncertainties in the calculation, and so on. Okay, I can also say here that often for proof of principle calculations or a first calculation of its kind, maybe the pion mass would be considerably larger than physical. Maybe these limits won't have been taken at all. And so then the error bars mean something very different. They mean essentially just this compared to a fully controlled calculation where maybe all of these have been taken into account in the error bars. Okay, so why did I say in a proof of principle calculation, you might set the pion mass to be larger than physical? So this brings us to the discussion of sort of what is hard and expensive and why. Okay, so as I sort of hinted by saying that you might take the pion mass to be larger than physical, light quark masses can be expensive. And by that, I mean, the lighter the quark mass, the more expensive the calculations can get. And this is because of the computing propagators stage, mostly. Computing the propagators is more expensive as the masses get lighter because you're inverting a matrix, the Dirac matrix, that gets closer to being singular as you make that mass lighter. And so you need to maybe be a bit more sophisticated with the algorithms you use. Instead of something like conjugate gradient to do the inversions, you have to do something like adaptive multigrid. Essentially, it's just a numerically harder problem to invert a closer to singular matrix. So computing propagators requires numerically inverting a matrix, the Dirac matrix, which gets close to singular, so it's numerically harder. Okay. The other side of the coin is that not only does it cost more to get the same statistics, but this might drive you to consider a larger lattice volume because the correlation length is essentially is set by the lightest state in the system. So essentially a pion if we're doing QCD. And so the finite volume effects are also set by that lightest state in the system. And so the lighter the state, the longer the correlation length, the bigger your finite volume effects are in some volume. So then maybe you'll use a larger lattice volume, which carries its own additional computational cost. So this is sort of secondary. Not only does it cost more to do the same number of calculations, but you might be doing more expensive calculations to avoid other systematics. So finite volume effects set by the longest correlation length, i.e. the lightest state, i.e. lighter masses, may lead to larger lattice volumes being needed for a certain precision. Okay, that's sort of a secondary point. As you might gather from that, large lattice volumes are also expensive. And this is really for essentially obvious reasons. You have a larger lattice volume. If you keep the same lattice spacing, you have a larger number of degrees of freedom for every field configuration, for every propagator, for every piece of the workflow. And so it's just computationally expensive. So a larger number of degrees of freedom for each configuration, propagator, and so on. Okay, going down to finer lattice spacings. Is also perhaps unsurprisingly expensive. So here it's not about increasing the number of degrees of freedom. If you keep the same number of degrees of freedom but reduce the lattice spacing, it gets more expensive. This is for mostly a reason of the generation of the samples, that the algorithm that's typically used, so this hybrid Monte Carlo algorithm or Hamiltonian Monte Carlo for generating the gauge fields, in some sense it's a close to local updating algorithm. So if you have a chain of samples and you need those samples to be decorrelated on some physical scale, say the size of a proton or something that you want to study, as the lattice spacing gets smaller, since the updates are close to local in some sense, it takes more and more updates in a very fine scale to decorrelate on this fixed physical scale than if you have a very coarse scale, where maybe you only need a few updates before you have independent samples. But if you have a very fine scale, you need many, many updates before you have independent samples. So this is a manifestation of what's called critical slowing down in this context. This is, someone asked me about machine learned sampling approaches instead of the more traditional Hamiltonian or hybrid Monte Carlo algorithms for sampling gauge field configurations. That's something my group has done a lot of work on, and it's really motivated by this problem. If you do something that's not an update-based sampling approach, then you don't have this growing of the number of samples you have to take to get independent samples in a chain, because you're not using a chain at all. And so all of these are things that are in some sense algorithm dependent. The types of machine learning sampling approaches that we're developing, they're not quite at the scale of state of the art yet, but they're very promising in potentially mitigating this sort of a cost. And so I'm sure you can see that potentially if you have better inversion algorithms, this becomes less of a significant cost. If you have better sampling algorithms, maybe this cost becomes less important, and so on. So the explanation here was that the hybrid Monte Carlo sampling algorithm which is used for generating the gauge fields, involves close to local updates. So you need more steps to decorrelate at some physically relevant length scale as the lattice spacing goes to small. So this is critical slowing down. Okay. Something else that becomes expensive is looking at large Euclidean times. We saw in the example of the pion, so last lecture, that you're really fitting Euclidean time dependence of the correlation functions to extract the physics of interest. And in that case, maybe we can even scroll up to the end of the last lecture. Recall this figure here. So this was the quantity that we constructed called the effective mass. This was the Euclidean time dependence. There was some contamination from excited states that weren't the physics we're trying to access here at early Euclidean times. And then here at later Euclidean times, this particular quantity effective mass flattened out to give the mass that we're interested in. And so we did a statistical fit to this large time behavior to extract the mass. Now going to later Euclidean times here, you can see in the cartoon, I drew the error bars bigger, and that's because it gets more expensive to get the same precision at later Euclidean times. Unfortunately, later Euclidean times is also where the physics emerges, and so this is a trade-off, right? So why do things get more expensive at later Euclidean times? So I sketched some of the arguments for this at the end of last lecture, but let me just recap. So the Euclidean time evolution dampens or suppresses excited states. But the signal to noise ratio degrades. So an easy place to see this is for the proton. If we look at the proton's 2-point correlation function, and we do this all at a very sort of sketch level. So a 2-point correlation function is going to look something like this. The sum over x is we're just projecting to zero momentum. There'll be 3 quarks at some position x and t, 3 antiquarks at some other position. We'll call it 0, 0. We integrate out the quarks. And we see that we can write this as 3 quark propagators. This is the sort of skeleton diagram that we saw. And we saw for the pion, and you can do exactly the same calculation, that this will look like some number and then decay exponentially with the mass of the proton, which I'm calling Mn here, in the exponent. So this is exactly what we saw for the pion, that this 2-point correlation function looks like something which decays exponentially in the large time limit with the mass in the exponent. Now, thinking about signal to noise ratios, what's relevant is not just the expectation value, but also the variance. So the variance of the correlator can be written in a usual way for a variance, right? And if we look at this term, and do the same sort of sketch of what we have there, we have not just 3 quarks and 3 antiquarks, but all of these guys, which in our skeleton diagram look something like this. Okay. And so these states, these 6 quark lines that I've drawn here, sure, I can arrange them to look like a proton and an antiproton. I can also arrange them to look like 3 pions. And since 3 pions are lighter than 2 nucleons, it's that state that will dominate this large time behavior of the variance here. So the states that propagate are n plus n bar, but also 3 pi. So the relevant exponentials here are both either minus 3 m pi t, as well as either minus 2 mnt, but 3 m pi is less than 2 mn. So the first term is dominant. So if we think about the signal to noise as a ratio, which will look something like expectation value of the correlator over the square root of the variance of the correlator, it looks something like this. So it grows exponentially as t gets larger. Okay, so we want to go to large Euclidean times to remove excited states. However, going to large Euclidean times, the uncertainties get bigger unless we do more and more measurements. Okay, I was also just mentioning excited states contaminating small Euclidean times. So those can get in the way. Often in discussions of state-of-the-art lattice calculations, the questions will be how were excited states taken care of? Was that analysis done carefully and appropriately? So these are damped out exponentially by Euclidean time evolution. As I mentioned last time, you can do a sort of variational method. So use a whole matrix of correlation functions, so using different operators at the source and sink, and basically solving a generalized eigenvalue problem to try to subtract out the excited states. You can do that. It's expensive. And it's expensive because instead of making one correlation function, you need a whole matrix. That's really the state of the art, though, especially for spectroscopy. You also do need to be able to write down operators that have good overlap onto the state you want to write down. And if you're studying something that's not a ground state, it's not necessarily obvious how to write down an interpolating operator that has great overlap onto the fourth excited state if you don't have a lot of physical intuition for what that state should be. So excited states need to be taken care of carefully. Something else that can get tricky is to look at large momenta. So this is again a signal to noise thing primarily. So for non-zero momenta, the signals scale with the energy at that boost. So for non-zero hadron momenta, the signal looks like e to the minus the energy. So this is momentum dependent energy times Euclidean time. But in the variance, so this is essentially the same argument that we went through just above about large Euclidean times. In the variance, the quark and the antiquark have opposite momenta. And P plus minus P is zero, of course. So the variance is still what it was before. So it's still e to the minus 3 m pi t if we're thinking about the proton. And so then in that case, the signal to noise looks pretty much like it did before, except with now this energy of the excited state, EP, for some particular boost momentum P in there. So it's worse with increasing momentum P. Okay. So quite aside from the signal to noise getting worse, you can also have a more dense excited state spectrum as you go to higher momenta, which can make it also harder to differentiate between your different energy levels. Okay, the other thing that can get very difficult, in fact gets very difficult, is to study nuclei. You get the same sort of signal to noise issues as you do for large momenta. You can write down essentially a very similar argument to what we wrote down here, but also the growth in the number of contractions that you have to make as you have larger and larger nuclei, so larger and larger atomic number, which is the number of protons and neutrons, is horrific. It grows factorially, and factorials grow really fast. So you can only sort of do calculations for very light nuclei with atomic number of a few, 2, 3, 4 at the current stage, partly because that number of contractions just grows horrifically badly. So nuclei have signal to noise issues. Like for large momenta. And you can just straightforwardly extend the argument we made, just add more quarks and antiquarks, QQ bars, draw the skeleton diagrams, work out the scaling of the signal to noise. But also the factorial growth in the number of contractions with atomic number, which can just be insurmountable. Okay, so these are the types of things that are difficult. And so that's why for a proof of principle calculation, and let me take an example, a proof of principle calculation of nuclei, also something that I work on, it's quite typical to use a single value of the lattice spacing, a single lattice volume, and to make the quark masses heavier than they are in nature, so that the calculations get cheaper, the statistics are better, and you can maybe actually see a signal, and then work down, so work towards complete systematic control. But first, for a proof of principle, go to a setup where it's computationally cheaper to demonstrate the technology. Okay, so what are the sort of typical scales of lattice calculations these days? Okay, so a lattice spacing that you'll see in sort of typical calculations at the moment is anywhere from 0.0 something Fermi, so now we're in physical units here, up to 0.1 and a bit Fermi in physical units. Lattice volumes as we discussed before, it's often written like this, L cubed by T, where this is the number of lattice sites in each spatial dimension. This is the number of lattice sites in the time dimension. Sort of at the small end these days, this could be 24 cubed by 48, up to something like 128 cubed by 256, or even larger. And just for a sense of scale here, if you're at this scale here, each gauge field configuration, each sample is really, really big. So if we do out the maths, you have 128 cubed by 256, but you have 4 space-time dimensions. And for each space-time dimension, you have, say, an SU3 or whatever your gauge group is matrix on each edge of the lattice. So we'll say we've got NC squared numbers. I'm counting here the number of numbers, or the number of degrees of freedom, times 2 for real and imaginary parts. So this works out to be something like 4 times 10 to the 10, which works out to be something like 320 gigabytes for a single gauge field sample, right? So you then have to, first step, sample several thousand of these, and each sample is ordered hundreds of gigabytes. Okay, number of samples. I already sort of implied this. This will be order 100 to 1,000 or tens of thousands. Number of measurements. So you might do multiple measurements on a single sample. So that would be, you can put the origin of your quark propagator at different points on the gauge field. And if they're far enough apart, they're statistically independent. And so you can have more measurements than you have samples. So this might be from 100 through hundreds of thousands of measurements. Quark masses. From something physical, like 140 MeV pion mass, through to, say, for nuclear physics, we're still doing some calculations with 800 MeV pion masses, so very far from physical, right, to do proof of principle calculations. Sometimes even lighter quark masses, you might interpolate the physical point. The number of flavors. Everything possible is done, so it might be 0 flavor, 2, 2 plus 1, 3, 2 plus 1, plus 1, 2 plus 1, plus 1, plus 1. So this notation that I'm using here, each number is the number of degenerate flavors. So this would be 0 flavors. This would be 2 degenerate flavors. This would be 2 degenerate flavors and 1 other flavor that's not degenerate with the first 2. So for example, you might have equal up and down quark masses and a strange quark mass that's different. 3, that would be, say, an SU3 symmetric. So you have 3 quarks and they all have the same mass. Here you would have 4 quarks. So 2 would be the same, say up and down. You would have a separate strange, separate charm, and so on, right? So this is how this counting works. And all possible combinations of this are essentially done. Oh, I should have put 1 plus 1 plus 1 on the list. And computing resources for small calculations, you might need a few million core hours. And for large calculations, so state-of-the-art types of calculations, this would be multi-year, hundreds of millions of core hours. And these are really sort of campaigns over many years or even over decades where generating the gauge fields is something spread out over. You'll generate gauge fields on some ensembles over some years, do analysis on those, then add additional finer lattice spacings or bigger lattice volumes or different pion masses to the set in later years so you can get better systematic control over time. Okay, so we have something like half an hour left. I want to talk a little bit about phenomenology. I had quite a few requests over Slack for different topics to cover. I had to pick just one. So I'll give you a very brief overview of some sort of phenomenology applications and then go into a little bit of detail on just one topic. So apologies if I didn't pick the topic that you suggested. Okay. For an overview, let me just write down some important topics. Okay, so thermodynamics. Oh dear, this one. Thermodynamics, there's a lot of active work. And if you're interested in overviews of these topics, there's an international symposium on lattice field theory every year called the Lattice Conference. So Lattice 2021, Lattice 2022, Lattice 2023, and so on. And there's always a series of plenary or overview talks and also proceedings coming from these conferences. And typically there'll be overview talks in most of these major areas every year, with typically a young person who's an expert in one of these areas, gives an overview of the state of the art of the field and writes a wonderful proceedings that really summarizes the state of lattice QCD for, say, thermodynamics. So if you're interested in more detail in these, that's a great place to look. But so the types of things people work on are getting a QCD phase diagram versus temperature and density, show the existence of a crossover to a quark-gluon plasma at some critical temperature. This is, of course, important to experimental programs, say at RIC, at Brookhaven. So that's the kind of programs that go on there. For precision flavor physics, this is an area where we're in an era of fantastic control on the lattice QCD side. So one of the big goals here is to constrain parameters of the standard model that encode the quark mechanism, so the CKM matrix. Once you have those, you can then go and make standard model predictions for other processes and search for BSN physics. So lattice QCD is really part of the state of the art in flavor physics and has been for a long time at this point. In hadron spectroscopy, so these are calculations like the one we did for the pion, but looking for, say, entire spectra of states of hadrons. The question is, can we understand the spectrum of particle states from the standard model? For the mass of the proton, can we get that really precisely? But what about all of the other states in the spectrum? What about states that aren't quark model-like? Can we understand exotic states? Can we understand glue balls? And so on. For hadron interactions and nuclei, can we compute how hadrons interact? How do nuclei emerge from QCD? Can we calculate nuclear reactions directly? The state of the art is there have been some proof of principle calculations of many aspects of nuclear physics, including nuclear reactions, interactions with electroweak or possible beyond the standard model currents, and so on. Everything I've said has really been fairly standard model biased because that's what I work on and I'm most interested in. But there are also many applications of lattice QCD to beyond standard model theories. So there are many interesting field theory questions beyond a perturbative regime. You might be interested in Technicolor, so strong dynamics and electroweak scale. You might be interested in studying supersymmetric field theories and so on. And so many of these theories, if you can formulate them like we've done, you discretize your actions, you can do lattice field theory calculations of them. Okay, so in my written notes, I have some more pointers on these topics and I can send you references for overviews of any of these if you can't find them, if you send me a Slack message. Okay, so I have a little bit of time to go into one example in just a bit more detail, which will hopefully make it a bit more concrete and real. So one of the questions was about some recent work on gravitational form factors. So this is particularly exciting right now because there's been some simultaneous development from theory, so lattice QCD calculations, and from experiment. And just in 2023, at the end of 2023, there were some of the first controlled lattice QCD calculations of some of these quantities called gravitational form factors, and the first experimental measurements of some aspects of those quantities sort of at the same time. And so it's been a really nice story of synergy between theory and experiments measuring, in this case, gravitational form factors of the proton. So what are gravitational form factors? If you are familiar with, say, electromagnetic form factors, those tell you about the structure of a state as seen by an electromagnetic probe, right? What's their coupling to a vector current, Q bar, gamma mu Q. Well, gravitational form factors tell you essentially what the name suggests. They tell you about the structure of the state as seen by a graviton probe, right? So graviton is J equals 2. So you have a tensor current. And so these are essentially related to matrix elements of the energy momentum tensor, just like electromagnetic form factors are related to matrix elements of the electromagnetic current. So they describe the non-perturbative information about the coupling of some hadron state to the energy momentum tensor of QCD. Okay, so in terms of matrix elements, what you're really looking at here are matrix elements of the energy momentum tensor. Right, we talked about you can calculate 3-point functions. So for example, matrix elements of local operators, this would be an example where we're going to access the relevant physics through a calculation of a 3-point correlation function. So those matrix elements tell you about exactly what the energy momentum tensor tells you about. So distributions of energy, spin, pressure, shear. You can separate out the quark and gluon pieces inside some hadron state. One of the sort of interesting qualitative things that's come out from both the lattice QCD calculations and the experimental measurements over the last year or so is that you can use all these different distributions, so like the energy distribution, to define different radii of a proton. And one of the interesting things that's come out is that these results suggest that gluon radii of a proton are somewhat larger than quark radii of the proton, which is a sort of new qualitative feature of the proton that we didn't know about before. Okay. Oh, just sort of an aside, I mentioned there have been experimental measurements and also that these tell you something about graviton scattering. Of course, you don't do the experiments by graviton scattering. You do them by using 2 photons to get to the same sort of J equals 2 state. So deeply virtual Compton scattering would be the sort of process you can use. But basically, you just need a J equals 2 current, and you can create that with photons instead of gravitons, since we can't do graviton scattering experiments. Okay, so what we want to do is calculate these gravitational form factors, which are related to matrix elements of the energy momentum tensor. So GFFs here means gravitational form factors. And they're related to matrix elements of energy momentum tensor. Lots of abbreviations in that sentence. So the energy momentum tensor, if you remember, looks like this. There's a gluon piece. And there is a quark piece. Sum over flavors here is what this F's doing. I have my quark field, psi F. D is a covariant derivative. So hopefully this looks somewhat familiar. It's just our regular energy momentum tensor. I haven't put it in Euclidean space. I haven't talked about discretizing these fields or anything at all. And I'm just defining for you what these gravitational form factors look like. I'm going to use a pion state for simplicity. And if I put the energy momentum tensor in between two pion states, you can write down what the decomposition into different Lorentz structures has to look like, essentially just by the various symmetries of the system. This for the electromagnetic form factors and exercise in Peskin and Schroeder, chapter 5 or 6, I think. But you can follow just exactly the same exercise here. Just let me write this down and then I'll explain a bit more. Okay, so here I've just put this energy momentum tensor wedged between pion states. This is at momentum P. This is at momentum P prime. I've defined capital P as the average momentum and delta as the difference, and T as minus that full momentum squared. Yeah. So these are just the only possible combinations of the available terms that we can write down that have all the right symmetry. So this is just doing a decomposition into the different Lorentz structures. And in front of the terms in those decomposition, we have what are a priori unknown coefficients that you can, again, just by thinking about symmetries of the system, you can see that they can only be functions of the squared momentum transfer. These things here, these are the form factors. So on Peskin and Schroeder, you do this exercise and you get out the electric and magnetic form factors. If you put an electromagnetic current in here, here we put in the energy momentum tensor, and we get out these things which we call the gravitational form factors. For the pion, there's just two. For the proton, there's additional one that has something to do with the spin decomposition. They're called A and D conventionally, yeah, for the pion. So this thing here, if T equals 0, this just tells you about the fraction of the momentum of the proton carried by quarks and gluons. If you look at the different pieces, if you put in the TG and the TQ in here separately, this will just be, actually it's roughly 0.5 and 0.5 for the quark and gluon pieces. Okay, so how do we go and compute now this A and this D from lattice QCD? So we're going to compute A pi, D pi. And of course, we'll compute them. We only have discretized values of the momentum transfer on our finite box. So they're at discrete T, since momentum is quantized in units of 2 pi over L. So T is the conventional name here for this momentum transfer for form factors. It's not Euclidean time. So just be careful here. I'm not talking about Euclidean time. I'm talking about this momentum transfer. Okay, so what does the process look like? We have to define discretized Euclidean energy momentum tensor operators. We have to choose operators that transform in safe, reducible representations of the hypercubic group. So they don't have mixings, power divergent mixings that we can't take care of. we need to define some sort of combination, it's typically ratios, of 3-point and 2-point correlation functions that allows the matrix elements that we want to be extracted. And I should say, for choosing operators that transform in safe irreducible representation to the hypercubic group, in this case, what that will look like is here, these operators have mu and nu indices. Some particular linear combination of different choices of mu and nu will be something that transforms in a hypercubic irrep. So you'll find that you'll do the group theory and you'll find that, oh, okay, I want to take some combination, say T11 minus T22, and that transforms in a safe hypercubic irrep. And I'll use that particular operator combination to do my calculations, right? Okay, so we'll define ratios that allow us to isolate the matrix elements. Then you'll solve a system of equations. For different matrix elements. So this may be different choices of P and P prime that give you the same momentum transfer T, maybe different operator components. You need to solve a system because you'll have some linear combination of A and D with different coefficients, depending on what P's go in here, what mu's and nu's go in here. These prefactors will be different. And so for each choice of P, P prime, and mu and nu, you'll have a different linear combination, and you solve those to extract A and D. Then you have to renormalize. Match to MS bar, and then repeat for different lattice spacings, volumes, bare quark masses, to extrapolate to the physical point. So that's the generic process. In the interest of time, I'm not going to go into how you discretize these operators. In fact, we've actually already seen it. So discretizing here, the covariant derivative, you can do a finite difference. You have to introduce a gauge link, right? Discretizing the gluon field strength tensor, we saw that too. We saw that when we were discretizing the action. So I won't go through that again. It's in my notes. If we calculate 3 and 2-point functions, so remember our 2-point function, we can write projected to some momentum at some source time. We can write a 2-point correlation function with some creation and annihilation operators, or we call them interpolating operators. So we here create a state at 0, we annihilate it at some later time Ts, we've projected to momentum P, and we saw before for the pion, we're still looking at the pion, that this looks something like a sum of exponentials. So some coefficients from the overlap factors, and then it's a sum of e to the minus energy in that tower of states times the Euclidean time, which here is Ts. Exactly the same exercise that we did previously to get this, we can also do for a 3-point function. To be really explicit about it, Here I'm inserting the state at time 0, space 0. I'm inserting the operator. So this operator here will be living in some irrep of H4. That's why I've put no indices on it, because I've chosen some combination of indices that lives in an irreducible representation. I'm annihilating at some later point in time. I'm momentum projecting to some momentum P prime, and I'm momentum projecting the operator insertion to some momentum transfer delta. So this is the same notation we used just before. Now, if you do exactly the same steps that we did previously to get this sort of a decomposition, you can see that this looks pretty similar. In this case, you just have to insert 2 complete sets of states to do out the maths. But I'll leave doing out that math as an exercise. You see that what you get is the matrix element that we're looking for. So here it's this matrix element of this energy momentum tensor between 2 different states, n and n prime in our tower of states, multiplied by some constants out the front and some Euclidean time dependence. The Euclidean time dependence here still carries energies of the various states in this tower. And so previously, when what we wanted to extract was the energy, okay, we can get that just from the 2-point function. Now what we want to extract is this guy, this matrix element. So we're going to have to divide out this Euclidean time dependence, right? So this is why ratios of 3 and 2-point functions are particularly useful. So in this case, the ratio that you write down, there are different choices, but one choice is to write down a ratio of 3 and 2-point functions that you're really designing to cancel off all of that Euclidean time dependence. It looks a bit complicated, but if you plug in those expressions above in this ratio, you'll see that by forming this particular combination with different Euclidean times and different momenta plugged into these 2-point functions, it simplifies down. And what you get is that the limit, as all of these different time scales, the source time and the difference between the source time and the operator insertion time, as those different time scales become large, this ratio here goes to the matrix element that we're interested in between the ground state. Plus some exponential contaminating terms. So this is the matrix element we want. There's some energies here. We have to get those separately and divide them out. This limit of this ratio is what we extract from fits, right? So this from fits to the TS and TS minus tau dependence of LQCD results. We get these from fits to C2. And this thing here, that's what we want. That is a linear combination of A pi and D pi. And it depends on P, P prime, and the operator. Okay, so that is, this gives you a system of equations that you need to solve. Okay, so I'm almost out of time in just the last minutes. So I want to show you what this actually looks like. So here I'm going to show you some data from what was actually the first calculation of the gluon GFFs. Which was 2018. I'm just choosing that because it's sort of easy to look at. So this here is the ratio that we were looking at. You see here, this is what we were calling TS, is called TF here in the plot. This is the operator insertion time tau. So if you remember the picture we had, we have some time 0, we have some time TF. In this case, it's a gluon operator, so the skeleton diagram looks a bit funny, but we're going to insert the operator at some intermediate time tau, and we should have signal for tau is between 0 and TF. If you insert the operator before you've created the state, you're not going to have a signal. Similarly after. So here tau needs to be between 0 and TF. You see here in this figure, well, there are two different TFs. There's 13 and 18. And 18 on the figure. And in fact, you see there's some exponential contamination from excited states. Then it reaches a plateau. And for different TFs, you have these different and longer plateau regions. So these are these ratios of C3 and C2. This is exactly the same as this, just plotted on a different axis. This is now showing it for tau equals 5 and 7 as a function of TF. And so we're inserting tau at some fixed time. TF better be later than that time, otherwise you won't have a signal. So tau's inserted here at 5 or 7. TF later than that time, you see this plateau. And so you're fitting to these plateau regions. It's a higher dimensional space, right? These are just different projections of the same data. These two panels are for different choices of operator. So for each of these, you fit, you extract some number, and all of those together give you a system of equations. So here, each band is from one ratio. These are just at different values of t, so different momentum transfer. Each of these bands is coming from a different fit here to a different ratio. You solve the linear system to extract D and A in each case. Remember, each ratio gives you some linear combination of D and A, which is hence a band on this plot. Okay, then you solve the system. This gives you a value for DNA at 1 GeV squared. This gives you a value for DNA at 1.53 GeV squared. You can plot those results as a function of that momentum transfer. So this here, that gives you this point here. And this one here, 1.53, gives you those points there, right? You do this for every different momentum transfer, and you can build up these form factors as a function of the momentum transfer. Okay, that was 2018. The first complete calculation was in 2023 with a lot of work done by one of my excellent students, Dimitra Pevku, who's now a postdoc at Berkeley. And I'm going to show you just two interesting figures here, and then we'll wrap up. So this is showing for the proton, you have 3 of these generalized form factors. You've still got called A and D, but there's an extra one called J. And you see here in this calculation, there's separate strange up, down, gluon contributions as well as the total form factors. In this figure, you see a comparison to experimental results. So these gray data points are the first experimental measurements of this form factor. You can see there's pretty nice consistency with the Lattice results. There's nice complementarity. Lattice has been able to go to much larger values of T. Experiment has a chance for more precision here at low T. This bigger gray band shows the systematics there. Here, the different colored bands come from different analyses of the same experimental results. You can see that the Lattice results here in blue agree much better with one particular analysis than the others, because the experimental analyses were somewhat model dependent. So again, sort of beautiful synergy between theory and experiment going on here. And I think I should stop here. So thank you very much. I'm happy to answer questions over Slack. I'm happy to send you references if there was anything that caught your interest during these lectures. Thank you. Bye-bye.